Hello everyone, welcome to the fourth part in this series on how to build a multicolored research-based Go playing program. So in this video we'll implement the rule of Ko. So the rule of Ko is the rule that prevents board positions from being repetitive. And yeah, without further ado, let's essentially get started. So I just go to the source code from the previous part, and I will probably like to adjust the position a little bit. So I don't want this one. I want to make this as black, and let's do go, build, and go. Okay, so the first position to have, let's replace these stones with a different color. Yeah, so now this is the perfect position. So let's say white would now take black, okay? And then black would not be capable of recapturing because of the rule of Ko. So say when white takes here, then this square 101 will become the Ko square, okay? And yeah, probably let's do this a little bit the opposite. So I would also like to make this one white, but this would be 100. Yeah, so black would be taking. So the core routine to distinguish whether the move is going to be the one that would reinitialize the value of Ko or not would be the function called diamond, and diamond shape is this 4 stones. So if we have a diamond of a given color, that would be one of the conditions for the Ko square to get initialized. So now we'll create a function that would be answering the question whether the given square is located within the diamond shape of same color or not. So without further ado, let's go and implement that. Okay, so just right in here, I want to say function and board pointer to board, we'll call it diamond. It would be taking the square type integer, and it will also return integer type. So this would be either black or white color, or no color or empty. It's also possible. So let's define variable called diamond color equals to -1. So we initialize this with let's say no value for now, and also other color, so the opposite to a diamond color, would be equal to -1. So we just initialize two variables. Then we want to define neighbors. So these are the squares we're supposed to be looping over. So this is the integer slice, and we could also define it. So this would be like 1, 1 -1, then board size, and minus board size. Okay, and then we want to loop over these neighbors. Okay, neighbor squares. So e equals to 0, e is less than 4, up to 4 elements, and e plus plus. So here we can ask if board position indexed by square, so the argument, this one, square plus, and neighbors indexed by I. So if this is equal to off board, then we just continue. Okay. Otherwise, it might happen that if board position and again square plus neighbors indexed by I is equal to empty. Then we want to return 0, or we can also say return empty, because empty is indeed equal to 0, but just to make it a bit more clear. So this is not the case we're interested in. And after this, in other cases, we know that there is a certain color that we do encounter, and whatever color we encounter first, we set this to a diamond color if diamond color is equal to -1. So this has not been initialized yet. And if this is the case, then indeed diamond color is going to be equal to board dot position indexed by square plus neighbors indexed by I, and respectively other color is going to be equal to, yeah, we are not assigning, so I can do like this. Okay, 3 minus and diamond color, so literally the opposite color. Okay, board position indexed by square plus neighbors and indexed by I equals to the other color. We also want to return 0, because this means that we have some stones of one color, some stones of another color. So in this case, we're not setting the code. Like in future, I mean, this is not, the square is not in diamond of a single color. Finally, we need to strip marker bits, because it might happen the marker bits would be right in there, because we might call this when we're counting the group with liberties. So it might not be the case, or it might be the case. So we want to bitwise or the diamond color with 3. And after this, we want to return the diamond color. Okay, so let's see if this still compiles. Okay, and now we will ask about the square 101. Okay, so I just want to do, so before showing the board, fmt.print, I can even do print line here, so board diamond and the square 101. And since the square is white, it should print 2, which is the value for the particular diamond shape. Yeah? So this is the value of 2. If one of them would be like another color, say this one would be black, we'll have 0. Okay, because it's not a diamond of a single color. Also, if this happens that there is an empty square, then also we don't have a diamond shape, so also return 0. Okay, now the most interesting part, we now need to alter our set stone a little bit to start making use of this diamond routine to figure out whether the co-square should be set or not. So you remember we got captures handling over in here. So here we want to add one more condition. So I ask if the length of board group is equal to exactly 1. So we're capturing 1 stone. If we're not capturing 1 stone, if we're capturing like 2 or more stones, this is not go anyway. So 1 stone, this is the first condition. But also, we need to make sure that board, diamond, and the square. But here is a little problem. The square, yeah, let me just do condition equals to 3 minus board size. In this case, we want to set the co, but board co equals to board group indexed by 0. So the square where the only stone was, that would become a co-square. But this square, we got a bit of a clash of variables. So this square we're sending to board diamond function is essentially this square. Okay, but we also have square here. So let's just search for all squares, and I would just rename this to S. Okay, S, and board count as 3 minus color. Okay. Okay. And then, yes, again, we would be counting like this one. It was working because the local square finished after this for loop, and then it was again the argument. Now it's more clear. So again, yeah, we have, when we loop over all the board squares to find groups that has to be captured. So now this is S, okay? And here still the square, essentially the square where user sets the stone. Right, so it should be okay by now. So still compiles, all right. Now, finally, what we want to do is want to play, just want to figure out which square I want to play in. So 101 to be played with black. Let's have a look. So play 101, and I want to play with black. Not quite sure why this one is done as a move. Let's make it just to set up the position. 1, 2, 2 equals to white. Yeah. So if I now did everything properly, it should. Okay. So something goes wrong. I did capture. Yeah. But co is not there. Oh, that's because not the board size, obviously, but the board size. What have I done? Okay. Yeah, now we got the co being initialized to Q16. So we've just captured the Q16, and now Q16 becomes co, which means that if we want to play with white over in there, those would be treated as an illegal move. Let's check this one last thing. So if I just yank, paste, and if we just try to play to 100s and with white, then this is not done, okay, because that move is illegal because we have co there. All right. So we may now assume that the rule of co is working properly, but again, this is not the way to test it, and obviously we need to make more tests, like to see how the snapback works, how killing the corner works, etc. So starting from the next video, we'll start implementing the GTP protocol. I don't know, maybe would make it in a single video, maybe it takes a couple of videos, I'm not quite sure. But the idea is that we now have all the rules of the game of Go being implemented. Well, there is also like superco and positional superco rules, which are the variations that do not allow to repeat board positions after a few moves, let's say, when you have multiple co's on board. But for now, we'll drop that because our engine is not going to be generating those like sequences. So no particular practical reason for doing this, at the very least at the moment, because that would involve the need of creation of hashing a board position. This can be done also. This is not that complicated, but for now we don't need that. I don't want to complicate things where it might be avoided. Okay, so Once we have the GTP interaction with the GUI, we would be capable of seeing whether some complicated positions that we can pass to the engine from the GUI would be synchronized. That's it from my side, guys. Thanks for watching, and I'll see you in the next video. Until then, and cheers.